Howdy folks, Mr. Reed here, and welcome to One More Question. So I'm going to be taking a look at how something moving in a circular path can be related to a sinusoidal function. So whether that be sine or cosine doesn't actually matter, but that nice waveform equation or graph that's made from the equation is actually something that we can match to at least part of the circle's motion, or something moving around a circle's motion. This can be really convenient for solving for particular things in problems where something's moving around in a circle. So if you'd like to see how to match up circular motion with a sinusoidal function, you're in the right place. So let's get to it. Okay, so this is actually done a little bit differently than normal. I think I'm just going to leave my little animation up above on a loop. And so if it becomes distracting, I'm sorry. Try to peel your eyes away from it for a bit once we get to the end. But I'm just going to let it loop through. And so what's happening in that animation that I made in Desmos is really cool. If you haven't experienced it, it's really good for just basic graphing, but you can do some nifty things in terms of setting up things with parameters and having it run through, well, what ends up being a little animation. So I have a circle that's actually, I made it so that it's off of the origin, put it a couple units to the left of the y-axis. That's a circle of radius 1, so it's basically a unit circle, just as I said, off of the origin. So I've labeled a point on that, and it's just going around and around and around of my circle. What I also have is a basic sine x function from, I guess my boundaries would be 0 to 6 pi for the x values that I'm putting it through, and the y values are just all the y values that would correspond to that for y is equal to sine x. Now, one of the things that you probably should have noted at this point, which is actually pretty nifty, is that the circle, the height of the point at any particular time perfectly matches the y value of the point that is going through the y is equal to sine x function. What that means is that the y equals sine x function is perfectly modeling the vertical location of that point at all angles, but we can make that angle kind of go along with some period or time if that's more convenient for us when we set up an equation. So this is actually just great from a math point of view, and without any physics understanding necessarily of why this thing is going in a circle, it doesn't actually matter. We can model the location of it, not just kind of sort of accurately. If it's moving in a perfect circle, it is bang on that the sine function or a cosine function would be able to perfectly show you exactly where that height was at any particular time. Because circles are symmetrical, top to bottom, left to right sort of thing, we would also be able to do this for the horizontal location while it's in a circle, but I'm just going to do it vertically at the moment because it matches up with my little animation quite nicely, and I don't want to set it up in a different way. So what I actually want to get at here is the fact that my circle has coordinates at all the points around it, because I'm going to consider it a unit circle even though I have it off axis. We have talked about how the x comma y values around that circle are equivalent to saying cosine of some angle, whether we're going to say, I guess, the reference angle that would be, or not even the reference angle, the angle in standard position that has a terminal arm that extends through that particular point on the outside of the circle. It would be located at cosine theta comma sine theta. So what we've basically said is that the y value can be modeled by a sine function. That's what this particular thing says, because if sine theta always matches up with y, then that means we're able to find out the y value on that circle with that sine theta function. Of course, because sine theta and cos theta are really just phase shifts of each other, we can always do either x or y, vertical or horizontal or vertical. It would be the other way around from the way I said it out loud. We can always do that with either a sine or a cosine function. So what I'm going to do is I'm going to say that we are going to model this circular motion by setting up and talking about a very generalized sinusoidal, sine in this case, function, where I don't, I need a little plus in there, where I don't I want to see what these different transformations, how that relates to circular motion. So we'll go through them one by one and have a little chat about that. So in my animation up above, I have a radius of 1 unit for the circle, and we have an amplitude of 1 unit for the sine function, and it matches up perfectly. If my circle was larger and I just used the plain old sine function, it would kind of get all like wonky and diagonal value or lines that would connect my location in the circle with my location in the sine function. We don't want that. So how do we get the sine function to perfectly map the position even if the circle is larger or smaller? Well, we do an amplitude change for our sine function. So in this case, we can actually say that the amplitude and the radius are basically performing the same duty. So if we want to describe the radius of the circle it's moving in, then we just set the amplitude of our sine function to be the same amount as that radius. Pretty straightforward, but very convenient, and that will set up that part. This is a little more complicated, the b value, because what we really want is a lot of times we're interested in rotating around a circle and it takes some amount of time. So we don't really want to discuss it as an angle, or it's not as natural to discuss it as an angle. So for instance, if I am talking about somebody that is going around a Ferris wheel, it would probably be more natural to me to say they've been on the ride for, I don't know, let's say 45 seconds, as opposed to they've been on the ride so that they've rotated through 815 degrees worth of angle. That just doesn't kind of fit as naturally into our concept of what that actually means. So what we do is we want to take things like a traditional b value, which I guess in the case of our base function would be 1, that causes there to be a period of 2 pi. But if we were to take that and stretch it, and we've seen that what happens is we stretch it by 1 over the b value, then we want that to be equal to something. Now, just for the sake of argument, let's say that we were on a Ferris wheel and it took us 80 seconds to go around once. So if I set my 2 pi times a stretch factor to be equal to 80, then what I could do is actually solve this for the b value. So I'll divide by 80 on both sides, multiply my b up, and so I'd be able to say that that's the same thing as pi over 40 when I simplify the fraction. So that would allow me to place a stretch factor into my b value, which would set my period equal to 80. And I could just use seconds for my unit of my variable, and then it would end up being 80 seconds, and then we could see how that would equate to the vertical position as we go around, for instance, this Ferris wheel. That's pretty cool. As long as you start getting really comfortable with that idea of how we can take a stretch factor and use it to make the period become what we want it to be, then that will go a little more smoothly. This one's a phase shift. I usually try to pick a function that allows me to avoid phase shift completely. If you're lucky, at time is equal to 0, the object that you're tracking will either be at 0 on its way up, it will be at the top, it will be at 0, or the middle of the circle, on its way down, or it will be at the very bottom. If you're at the middle, or 0, on its way up, and it might not be 0, I guess I probably shouldn't say that. It's 0 for the circle that I have above, but if your circle was not laying on your x-axis, it would be the middle. So the middle going up, a sine function would model that perfectly because that's what it's doing at your 0 degrees or 0 radians. If we wanted to match that up with being at the top, a cosine, a positive cosine function will do that. In the middle going down, a negative sine function will do that. At the bottom, a negative cosine function would do that. If I said for the third one that it was cosine, it's actually negative sine for the middle on its way down. Second guessing myself, but I don't want to restart. So hopefully you can make that adjustment if I had made the mistake. All right, so I try to make my thing phase shiftless if I can. If instead it says, well, you're at the top 2 seconds after the starting time, well, what that would mean is we're kind of hanging out here, going up and down in terms of our sine and cosine function. It looks like a cosine function, but it's been shifted 2 seconds or 2 units to the right. So in order to do that, I could make my C value equal to 2, and that would fix it all up. So even if it's not on one of those nice ones, we can still pick a point that is probably described for us in the setup of the problem, and allow us to shift to that properly left to right by using that phase shift. All right, last up, we have the D value here, and this is going to be convenient if you can actually always ignore the D value and then adjust your answers afterwards, but it kind of makes more sense for your function to pump out the correct values. For instance, if we had some circle that was being done underneath of water, and we wanted to track how far underwater you were, you might set the surface of the water as being 0 for your height. So you just get a negative answer, and you can see very clearly that whatever the negative answer is for that height, it's going to be equated to how far below the level of the water you are. So in a case where the axle of the wheel might be, for instance, 15 meters below the water, then we would just say minus 15 for the D value, and then it would keep track of your height relative to that water surface, which can be really convenient for kicking out answers. All right, so that's basically the relationship to something that moves in a circle when you pair it up against a sine or a cosine function. So sinusoidal functions are really convenient for things that are experiencing circular motion. And if you want to see that actually done in the context of a problem, you pay attention in my next video, because that's what I'm going to be doing in just a few moments. So hopefully this one was good for seeing why you might be able to do it. And if you found that one helpful, like, subscribe, and as always, take care, folks.